Last time we introduced the concept of a maximum flow problem, which works with a special type of directed graph called a flow network. Every flow network contains a source vertex S and a sink vertex T. And the goal of a maximum flow problem is to route as much flow as possible from the source vertex S to the sink vertex T while respecting various constraints. For example, each edge has a maximum capacity, a maximum amount of flow that can be pushed through that edge. And the vertices in between S and T, the intermediate vertices, require what's called conservation of flow, which says that the amount of flow entering any intermediate vertex must equal the amount of flow that leaves that intermediate vertex. And we made some progress towards an algorithm that could compute maximum flows, but we hit a bit of a snag because although we reached a point where this algorithm would stop, that is, it wouldn't be able to push any more flow through the graph, we weren't able to assert that when it stops, the state of the flow at that moment truly is a maximum flow, only that it appears as if we can't increase it. So as a result, we weren't able to prove the correctness of our algorithm. So I guess those are on the agenda for today. We want to be able to show when a flow is truly maximum, to recognize a maximum flow. And also, we would like to conclude that this algorithm actually is correct, or fix it if it turns out that it's not correct. I can't help but think that there was something else we had to get to today. Oh yeah, that's right. So vertex T here is still on fire. So I guess we do need to put out that fire at some point in the near future. So what we saw last time was that the Ford-Fulkerson algorithm can be used to route flow through a network, and recall that the way it does this is it looks for an augmenting path. So it looks for some path from S to T. Usually it uses a construction called the residual network, or we can visualize it as doing so. It looks for a path from S to T where there is available capacity, what we've been calling residual capacity, that allows extra flow to be pushed. So one example of an augmenting path might be the path from S to V1, from V1 to V2, from V2 to V3, and then from V3 to T. For this particular augmenting path, the largest amount of flow I can push through it at the moment is 5 units, because if I push 5 units, some of the edges along the path become saturated, which means if I were to push any more than 5 units, I would be violating the requirement that the amount of flow along every edge not exceed the total capacity of that edge. And the Ford-Fulkerson algorithm just keeps looking for augmenting paths and performing augmentations until no augmenting paths can be found, and then it stops. And every time we tried it last time, it looked as if when it stopped, the flow was maximum. Like it looked as if there really was no way of pushing more flow through. And we saw a bit of a hint in one example we did last time of a way of recognizing that the flow is maximum. But ultimately, we weren't able to prove that the Ford-Fulkerson algorithm always produces a maximum flow. Now, even though we didn't have a proof of correctness, we did spend some time analyzing the running time of the Ford-Fulkerson algorithm, and we discovered something sort of unsettling there as well, which is that the running time isn't necessarily polynomial in the input size, that is, the number of vertices or the number of edges in the input graph. Now, that by itself isn't the end of the world. What was sort of weird was that the running time was parameterized by the value of the flow that the algorithm found. In other words, it was parameterized by a parameter of the output, which means we actually don't in general know what the running time of the algorithm is going to be until after the algorithm is done. So we can't even try to check in advance whether it's a good idea to run the algorithm because the running time might be too high. There's no way of knowing how long it'll take until we actually have the answer it would produce. And last time I observed that a similar case, although not as severe, would be that algorithm we looked at when we talked about dynamic programming to compute the answer to the subset sum problem, where that algorithm also wasn't polynomial in the input size because it was parameterized by this value w, which was one of the input values, but not the size of the input. So if a very large value of w, which was the goal sum in the subset sum problem, if a very large value of w were given, the algorithm could take a really long time, a time that could be exponential in the input size. That was less of a problem than this, because at least then, when you're thinking about using that algorithm, you know in advance that you should take a look at your value of w, and if it's too big, you should be careful. Whereas for the Ford-Fulkerson algorithm, we don't know in advance what the value of the flow computed is going to be, because if we knew that, maybe we wouldn't need to run the algorithm at all. So I suppose it's worth looking into whether there is a different algorithm or maybe a way of fixing the Ford-Fulkerson algorithm such that it runs in polynomial time, or at least runs in some amount of time that we can predict more easily. We don't want to contend with this hazard of the algorithm taking an incredibly long time for reasons that we're not able to see in advance. Now, I don't know about you, but I'm sort of new to the task of firefighting, and it's important to me, and I think maybe you'll agree with me on this. I don't think we want to put our professional reputations on the line, go charging into this firefighting problem, only to have all the other firefighters laugh at us because we're not using a polynomial time algorithm, and even worse, because we can't even prove the correctness of our approach. So I think it makes sense to take a step back, to relax a bit, not to panic, and to see if we can first prove the correctness of the algorithm, figure out what a maximum flow truly is, and then maybe see if we can find a more efficient algorithm before we go in and try and put out any fires. Okay, so to do that, I'm going to rewind back to an observation that we made about 3/4 of the way through the previous lecture. We saw a case in the previous lecture when we were computing flows where we were able to assert that a particular flow was maximum. And it basically came down to this observation. What we noticed was at a particular point in our algorithm, we had this collection of vertices that were reachable from S. So if we go looking for augmenting paths, we might find a collection that looks sort of like this. And we also noticed that if we looked at all the bridges leaving that cluster, all of them were saturated. And I made the observation that if all of those bridges are saturated, literally any flow that I could ever plan to route from vertex S would need to cross one of those bridges. Those are the only ways to get from S all the way to T. And if all the bridges are saturated, well then I guess there's literally no way I could ever push any more flow through the graph. I want to generalize that insight. I want to turn it into something formal that we can use. To do that, we need some definitions. I'm going to begin by defining something called an ST cut, which is a pair of two sets, S and T. Okay, so maybe you can see how this might cause some confusion. Surprisingly, it doesn't cause as much confusion as you might think. So notice how, of course, the traditional name for our source vertex is lowercase s. The traditional name for our sink vertex is lowercase t. And yet here, I'm defining these two sets, uppercase s and uppercase t. Okay, so bear with me for a few slides. I think you'll eventually find that it's not too big of a deal to do this. So an ST cut is two sets S and T, which partition the vertices of my graph. So every single vertex must be in one of S and T, and no vertex can be in both of them. So their union is the entire vertex set of the graph, and their intersection is nothing. Additionally, we impose the constraint that our source vertex must be in the set S, and our destination vertex must be in the set T. It is not a valid ST cut if I ever notice both S and T in the same of the two sets. So they can't both be in S, they can't both be in T. The source vertex must be in S, the sink vertex must be in T. Notice that one way we could read this definition is that once I've defined the contents of S, the contents of T is just everything else. So the vertex set minus the contents of S. Now, the term cut is used in other contexts in graph theory and graph algorithms. So if you think back to our study of minimum weight spanning trees, we talked about something called the cut property, which I think pretty clearly isn't really related to the problem we're talking about today. So that means that the word cut has a variety of different meanings. So that means that an ST cut in general might not be the same thing as a cut. However, I'm going to define, for the purpose of all of our discussion of flow networks, so for example in these slides, if I use the word cut, I am referring to an ST cut unless I explicitly say otherwise, because I'm going to refer to a lot of these things in the next few slides. So in this diagram, I have defined the set S to contain the source vertex S and vertex V1 and vertex V4. And I've defined the set T to contain everything else. And if you want a full listing, there it is. I'm going to establish a visualization convention right now, which is that every time in these slides that I want to draw or represent an ST cut, I will do it the same way. I will always shade the vertices in S in green. Every vertex that is unshaded is to be interpreted as being part of T. So I won't bother shading both sets because that becomes a little bit cluttered. Instead, all I will do is shade the set S. And remember again that the source vertex S is always in the set uppercase S. Okay, so now a few definitions. The first definition I want to give is basically a generalization of the capacity of a single edge to the capacity of a set of edges. In this case, it'll be all edges crossing from my set S into my set T. And one thing that we should observe right off the bat is I am not considering edges that cross from T into S. Only edges leaving the set S are considered by this definition. So the capacity of an ST cut, which I use this notation to denote, is the total capacity of all edges going from the set S into the set T. In other words, it is the sum of the capacities of all edges UV, where U is an element of S and V is an element of T. Now that I have a notion of capacity, I'm also going to define something called a minimum cut. A minimum cut is some ST cut that attains the minimum possible capacity of any cut in the graph. So if I go work out the capacity of this cut here, and it turns out that the number I think is 30, so 7 plus 1 is 8 plus 9 is 17, plus 3 is 20, plus 10 is 30. I don't count these two edges because they enter the set S, not leave it. Okay, so the capacity of this cut is 30. One natural question might be, hey, is the cut that I found here, is this a minimum cut? So one way you could disprove this is just to go find some other valid ST cut that has lower capacity. And so here's one of those. Here I've defined the set S to just contain the source vertex and nothing else. This cut has capacity 20. So there's 10, total capacity is 20. And clearly, if I have a cut with capacity 20, this cut that I had earlier is not minimum because its capacity is higher. Here is a cut with total capacity 58. If you would like to verify that the capacity is 58, you are welcome to do so as an exercise. I don't know if I want to risk doing that much math on a live recording. Here is a cut with total capacity 28. I want to pause here and just make also a visual observation. So because of my technique of using green outlining to denote what's in the set S, it's sort of easy to get confused and think that there's some requirement. Notice how the green outline here is some contiguous polygon. Maybe you'll be fooled into thinking that just because I use the single green outline around all the vertices, that there's some requirement that the vertices in S be connected to each other, but that is not the case. The only requirement of our ST cut is that it's a partition of the graph where in every valid ST cut, the source vertex is in S and the sink vertex is in T. So although it's sort of nice, it's aesthetically pleasing to draw a single connected outline, there's no requirement that the vertices inside of the set S or the vertices inside of the set T be connected to each other in any way. So this is a valid cut. In this case, the set S consists of my source vertex as well as the vertex V5 and the vertex V6. Okay, and so the capacity of this cut is 28. So there's 10, that's 20, there's 4, that's 24, another 4 brings us to 28. There are a whole bunch of other edges involved, so lots of other edges cross the boundary, but all of them cross into my set S. So this edge here, this one, this one, this one, and this one, all of those edges just cross into S, and so they do not contribute to the capacity of the cut. Here is a cut with total capacity 17. This one's sort of neat because you'll notice that every single edge between S and T does point from S into T. There are no edges pointing backwards. That's mostly just a coincidence, though. The total capacity here is 17. And then this cut here has total capacity 19. Okay, so maybe a quick comprehension exercise before we continue. So quick exercise is, go and find me a cut that has capacity less than 19. That's a way of demonstrating that the cut I've shown here, which does have capacity 19, is not a minimum cut. So pause the video and try that. One option would be to compute a cut from scratch, but there might be an easier way if you just rewind a little bit. The key thing to understand is if you are presented with a particular ST cut and you're asked to prove that it's not minimum, all you have to do is go find a cut with a smaller capacity. Now suppose you're given a cut and you're asked to decide whether or not it is minimum. Well, certainly if it isn't minimum, you could find a cut with lower capacity, but what do you do if you can't find a cut with lower capacity? What if you suspect it is a minimum cut? You know, this sounds a lot like the problem of deciding whether a flow is maximum. If I have a flow and I want to ask if it's maximum, well, it's clear if the flow isn't maximum because I could find an augmenting path. I could increase the value of the flow. But what if I can't do that? How do I know that the flow is truly maximum just because I can't find a way to increase it? It sounds a lot like the problem of, here's a cut, tell me whether it's minimum or not. Just because I can't find a cut with smaller capacity doesn't necessarily mean that one doesn't exist. So we end up in almost the same problem with cuts as we do with flows. I want to define more terminology before I address that question further. So I already defined the notion of the capacity of a cut, and I presented that as being a sort of generalization of the capacity of one edge to a set of edges, the set of all edges crossing from the set S into the set T. I want to perform a similar generalization, but with flows. So recall that we formally think of a flow as a function FUV, where the value of FUV is the total amount of flow across the edge UV. I now want to define the flow across a cut, or the net flow from S to T. Now, unlike my generalization of capacity, this is going to take into consideration flow passing in both directions. So the flow across the cut is equal to the total amount of flow leaving the set S, so the flow across edges UV, where U is in S and V is in T, minus the total amount of flow that re-enters, so the amount of flow across edges VU, where V is in T and U is in S. And so we can think of that intuitively as the total amount of flow exiting S minus the amount re-entering it somehow from T. All right, so you'll notice on the previous couple of slides, we actually had a zero flow, but on this slide, I actually have some actual flow assigned to certain edges. The value of the flow overall, which is pretty clearly not a maximum flow, the value of this flow is 3. If I want to go compute the amount of flow across the cut, so here's my set S, and that means the set T is everything else. If I want to compute the value across this particular ST cut, what I do is I add up the total flow across edges leaving S, and I subtract off the flow along edges that re-enter S. Okay, so the total amount of flow leaving S is 0 plus 0 plus 0. That's pretty easy, that's 0. Plus 0 plus 1 plus 1 plus 1 is 3. That's sort of weird. So the value of the flow globally, the total amount of flow reaching vertex T, just happens to equal the total amount of flow across this particular cut. That's sort of neat. Okay, here's a different cut. So same graph, same flow, but different choice of S and T. And so if I compute the flow across the cut, well, it's going to be 1 plus 2 plus 0 plus 0 plus 0 plus 0 is equal to 3. So the flow across the cut is 3 here as well, which also happens to equal the value of the flow. It's sort of an odd coincidence. Okay, here is a different choice of cut. So if I ask for the total value across the cut, that's going to be the sum of all the flow exiting the cut, so that exiting the set S, so 0 plus 0 plus 2 plus 1 plus 2, that would be 5. And then I want to subtract off all of the flow that enters the set S. Okay, so that would be there's 1 there, and all the other edges have 0 flow into the set S. So 5 minus 2 is equal to 3. So again, the flow across the cut, the net flow from S to T, is equal to 3, which again equals the total value of the flow reaching the destination, the sink vertex T. Here's another cut where again the flow across the cut is 3. 1 plus 1 plus 1 is 3. Here's another cut, and notice how in this cut I've managed to isolate the vertex V2 surrounded by vertices of S. Okay, so if I go to compute the flow across the cut, so the total amount of flow leaving the set S is 0 plus 0 plus 1 plus 1 plus 1 plus 1. That would be 4. So I've got 4 minus the total amount of flow that is re-entering the set S, and that would be along this edge here. So along the edge V2, V5, 1 unit of flow is entering S from T, and so the flow across this cut is also equal to 3. If this turns out to be a coincidence that the flow across the cuts always equals the value of my flow, then it certainly has become rather eerie. So in this case, as I mentioned, the total amount of flow leaving the cut is 4, but then 1 unit re-enters the set S, and so we don't count it. So we net out to 3. Notice that regardless of the choice of cut, the flow across the cut actually equals the total value of the flow, the total amount of flow reaching vertex T. Now, we should be careful in general about things like this. Just because I can show you a bunch of examples where something holds doesn't always make it true. I mean, I could have rigged the examples, but it actually does turn out that this is true in general. If you choose a valid ST cut and you have a feasible flow, it will always be the case that the flow across the cut equals the global value of the flow. There's a pretty easy intuitive justification, which is we know that because the source vertex S is in the set S, and because the sink vertex is in the set T, that all of the flow that leaves the source vertex S, which ultimately is where all flow comes from, because we can't have flow originating anywhere else because that would violate conservation, all of the flow that leaves the source vertex S and eventually gets to the vertex T needs to exit the set S and not come back. I mean, flow that exits the set S and then loops back around again doesn't count because we don't know what's happening to it. But all the flow that gets to T has to at some point leave the set S for the last time. And so I guess it makes some sense that no matter what you choose as your cut, as long as the cut is defined according to the definition, that the value of your flow globally will equal the amount of flow that is leaving the set S, the net amount leaving the set S. So I'm going to state that as a lemma. I'm actually not going to write a formal proof of that. I don't think that it needs a formal proof. I actually feel like basically maybe one or two sentences might be necessary to take this to generalize this intuitive observation. And because it turns out that the formal proof is pretty tedious. If you want a formal proof of this, though, you could create one pretty easily. So it's within your abilities. All you really have to do is use conservation rules. So basically what I'm actually saying is that the total amount of flow, as we know, reaching vertex T, or the total amount leaving vertex S, both of those are going to be equal to this if I have a feasible flow. We can employ conservation rules to show that the total amount of flow that leaves the set S and doesn't come back also has to reach eventually vertex T, basically. In any feasible flow, all of the flow leaving S must reach T, and therefore the net amount of flow that leaves my set S needs to equal the total value of the flow. One thing, however, to parse about this, something you ought to consider for the future, is that the lemma requires that the flow be feasible and that the ST cut meet the criteria. So if I were to define an invalid ST cut, so something where both S and T are in the same piece, so if they're both in set S, for example, or if I were to talk about a non-feasible flow, so a flow, for example, where conservation is not obeyed, this lemma, it might not hold. I encourage you to think of cases where this lemma wouldn't hold for flows that don't meet this criteria. All right, so since for any ST cut, the source is always in S and the sink is always in T, the capacity of the cut limits the total amount of flow that I can route from S to T. Because it doesn't matter how I choose the cut, ultimately, all of the flow that leaves S and finally arrives at T needs to exit the green shaded region somehow. So if I look at all the edges that leave the set S, which of course together they comprise the capacity of the cut, of the ST cut, all of the flow that gets from S to T needs to use one of these edges. What that's telling me is that the capacity of any cut limits the total amount of flow that can go from S to T. No matter how I choose the cut, if I look at all the edges that leave it, any flow from S to T must use those edges, and therefore the capacity of that cut limits the total flow I can get from S to T. Okay, so the slides are now confirming what I just said. And that leads us to a theorem that I'm going to call the weak duality theorem. In the slides to come, we're going to see another theorem. It's also a form of duality theorem. See if you can guess what the next theorem is called. We're going to see another theorem that I'm going to claim is a very profound result. I want to acknowledge right off the bat, though, that the weak duality theorem is going to do a lot of the work of the more important theorem for us. That is, when it comes time to prove the more important theorem in a few minutes, really, most of the work behind the scenes will have been done by this one. So this one deserves a bit of credit. The weak duality theorem says that if you have any feasible flow and any ST cut, so that is to say, the flow meets all the constraints and so does the cut meets all the requirements of the definition, then it will always be the case that the value of the flow is less than or equal to the capacity of the cut. And this is pretty easy to justify. So basically, using a combination of the things I've just said, we can justify this pretty easily, which is that any flow that gets from S to T needs to pass over some combination of the edges leaving that cut. And so if all of those edges are full, then no more flow can go from S to T. So if I happen to saturate every single one of these edges, then there is no way that any flow could exist that uses any more, that I couldn't push even one more unit of flow from S to T. And so what that's telling us is, if I look at the capacity of any cut, that is going to give me an upper bound for the value of any flow. And so basically this follows from the two things I observed earlier, from the fact that the value of any flow is equal to the amount of flow across any cut, and the fact that the amount of flow across a particular cut cannot be greater than the capacity of that cut, which I view this to be a natural generalization of one of the basic constraints that we defined last time, which is the amount of flow across an edge cannot exceed the capacity of that edge. All right, so now if we go back to looking at different cuts of this graph, here is a cut with total capacity 10. And we've looked at a variety of different ones recently, and this is the one that has the lowest capacity of any other one that we've seen. We've seen ones with capacity 30, we've seen ones with capacity 20, we've seen one with capacity 17, but this is the first one we've seen with capacity 10. So here's a cut with capacity 10. In the previous lecture, on the same graph, we actually found this flow here, and the value of this flow is equal to 10. Now, notice that if I look at that particular cut, the cut I just chose, all of the edges leaving the cut are fully saturated. So the capacity of the cut was 10, and all 10 units of flow from S to T, of course, have to pass over those edges, and all of those edges are now saturated. By the weak duality theorem, because we know that the value of any flow is less than or equal to the capacity of any cut, then the fact that I've found a cut with capacity 10 and I've found a flow with value 10 means that this flow is maximum. There is no way I could ever find a flow with value 11 because weak duality tells me it's impossible. But it also tells me that this cut has to be minimum. There's no way I could ever find a cut with capacity 9 because weak duality says it's impossible. So notice how I had these two problems. I want to know that a flow is maximum. Just because I can't find a way of pushing more flow through the graph doesn't inherently mean it's maximum. I also wanted some way earlier of determining whether a cut was minimum. I know a way of showing that a cut isn't minimum. I could just find a cut of smaller capacity. But when I have a minimum cut, how do I know that it's minimum? And weak duality actually gives me, in this case at least, one way of showing that. If I find a flow and a cut where the value of the flow is the same as the capacity of that cut, automatically the flow is maximum and the cut is minimum. Now, as usual with minimums and maximums, I need to observe that there could be ties. So there could be multiple different cuts with the same capacity in a graph. So I've got this cut and this flow, and the flow has value 10 and the cut has capacity 10. So I could also have this cut here. So this cut also has capacity 10, and so it's also a minimum cut. And I could also redirect some of my flow. So I've got this flow that I was already working with. If I change it slightly, here is another flow with value 10. So this is also a maximum flow. There could be multiple maximum flows in a particular graph. There could be multiple minimum cuts. And so one thing that follows naturally from weak duality is that if I have a feasible flow and some ST cut, and I observe that the value of my flow equals the capacity of that cut, then automatically F is a maximum flow and ST is a minimum cut. But this leads us to a question. So for this particular graph, I was able to find a flow with value 10, and then somehow I was able to find a cut with capacity 10. And that means for this graph, I know for certain that this is a maximum flow, and that the cut that I found was a minimum cut. That was maybe lucky though. How do I know I have that property for every graph? Maybe I could hand you a graph where the maximum flow has value 10, but the minimum cut has value, I don't know, 1,000 or something. So if I'm in that situation, how do I know that the flow is truly maximum? I certainly know it's maximum if I can employ weak duality, but if I can't, if I ever had a graph where the minimum cut had capacity 1000 and I'm looking at a flow with value 10, how do I know there is going to be a flow with value 1000? Maybe there isn't. The weak duality theorem doesn't guarantee me that the situation will always arise. I was lucky that it arose on this graph, but the weak duality theorem by itself doesn't guarantee me that for every graph I'll be able to find this pair of certificates. What I really love about this situation is because I have this flow and this cut, each of them, the fact that I have both of them in hand helps me prove, if I want to think of the value of the flow being maximum, the cut proves it. If I want to show that the cut is minimum, then the flow proves it. And so the question is, can I assume that I'll have this situation for any flow network? And the answer is yes. It leads us to something that I'm going to call the max flow min cut theorem. Now, the slides are going to say this in a few minutes, and so I'll give them their chance to speak, but this theorem is a really big deal. So the max flow min cut theorem says that for any flow network G, the capacity of a minimum cut always equals the value of a maximum flow. So this is a way of strengthening our weak duality theorem. So weak duality said that the value of any flow is less than or equal to the capacity of any cut. It doesn't guarantee that they're going to bump into each other, that they're actually going to have the same value eventually. But the max flow min cut theorem says that there will always be a flow and there will always be a cut where the value of the flow is equal to the capacity of that cut. And in turn, weak duality then guarantees you that this flow is a maximum flow and this cut is a minimum cut. Of course, I also have to observe that there could be graphs out there where the value of a maximum flow and the capacity of a minimum cut are 0. Quick little exercise to try on the side. Try and construct such a graph. And I don't know, for bonus points on this exercise, see if you can construct such a graph where it's not obvious just by glancing at it that it's going to have this problem. So we could also call the max flow min cut theorem the strong duality theorem. As I said a minute ago, it is sort of an upgrade on the condition provided by weak duality. And it actually turns out the reason I want to mention that, in fact, the reason that I gave the weak duality theorem a name to begin with, is it turns out that there are settings in which you would call it the strong duality theorem. But it is the case that in an algorithms course like this one, and if you open up an algorithms textbook, it's pretty much always called the max flow min cut theorem. That's what we are going to call it. I want to talk briefly about this idea of calling it the strong duality theorem because it takes us back to a topic that I love bringing up, which is linear programming. So I've mentioned that a lot of the optimization problems that we've tackled, not all of them, but some of them, have actually been a way of framing a certain form of linear programming problem. I'm certainly not done talking about linear programming in this course, but it actually turns out that there is this major theorem in linear programming called the duality theorem, and it also breaks down into weak duality and strong duality. And it's a statement that applies to all linear optimization problems, including the maximum flow problem. And so actually it turns out that what we are stating as the max flow min cut theorem actually is a special case of the more general duality theorem of linear programming, or for those that break it down into pieces, the strong duality theorem. So we could, by contrast to weak duality and by analogy to linear programming, call this thing the strong duality theorem. But in any event, I'm going to call it the max flow min cut theorem, and you'll find that in the world of algorithms, that's typically the name that's used, unless you're taking a linear programming course, which I hope that one day you do. So the max flow min cut theorem says that it is always possible to prove that a particular flow is maximum by finding a cut such that the value of the flow equals the capacity of the cut. There will always be such a cut. And similarly, if you want to prove a particular cut is minimum, just go find yourself a flow that has the same value as the capacity of that cut. So the max flow min cut theorem guarantees you that you will always be able to do this. Now, we already know that from the weak duality theorem, as we saw in the example a minute ago, that if we happen to find a flow and a cut where the value of the flow equals the capacity of the cut, we know the flow is maximum and the cut is minimum. So to be clear, the max flow min cut theorem isn't what tells us that. The max flow min cut theorem tells us there will always be such a flow and such a cut. Not that when you find a flow and cut with the same numbers, that means that you've got maximum flow and minimum cut. The max flow min cut theorem just guarantees that for any graph, you will always be in that situation. You'll always be able to find such things. So to prove the max flow min cut theorem, if we begin from knowing that weak duality holds, all we really have to show is that there always exists a cut whose capacity equals the value of a maximum flow. We do not have to deal with the case where the value could exceed the capacity of the cut, because weak duality has shown us that that's impossible. Okay, so the max flow min cut theorem, in my mind, is the most powerful and the most profound theorem that we have seen and will see in this entire course. That is how important I think it is. And so, of course, that means that we have to actually give a proper proof of that theorem. Now, we're going to give a very unique proof, and this is actually a style of proof that is also used often to prove the duality theorem in linear programming. So it's a technique that's sort of odd on its surface, but it's going to be quite clever from our point of view because it actually takes care of two issues that we have outstanding. We're going to prove the max flow min cut theorem by reasoning about the behavior, the hypothetical behavior of the Ford-Fulkerson algorithm. What's nice about that is that once we're done, we'll actually have in hand also a proof of the correctness of the Ford-Fulkerson algorithm. Okay, so the theorem is that for any flow network G, the capacity of a minimum cut equals the value of a maximum flow. Okay, so to start with the proof, let's let G be a flow network, and now let F be a maximum flow. And there's something that I have to, there's a sort of notational quirk, I guess, or a definitional quirk here that I have to expand upon because it's going to come up again in a minute. So I'm saying let F be a maximum flow. I'm not talking about how we found that maximum flow. I'm saying you give me a maximum flow on this graph, I will show you that there is a cut whose capacity equals the value of this flow. So we're not at the point where we're looking for a maximum flow. You're handing me one, and I'm going to look at that maximum flow and talk about it. Now, so here's something we know about maximum flows. If the flow is maximum, there is definitely no way to push any extra flow from S to T. I hope that's not a controversial claim. Clearly, if my flow is maximum, there's no way to increase it. Therefore, there can't be an augmenting path because an augmenting path is a way of increasing the value of a flow. So since F is a maximum flow, there are no augmenting paths in G. Another way of framing that is the vertex T is not reachable from the vertex S in the residual network. Okay, I want to come back again to this idea of me defining a maximum flow, just so that you don't mistake what I'm doing here as being some kind of circular reasoning. So do we know as of this moment, as of slide 48, have we yet seen evidence that if there are no augmenting paths, that we must have a maximum flow? So the answer is actually no. We saw in the last lecture that it appears to be the case that if the Ford-Fulkerson algorithm reaches a point where no augmenting paths exist, it does seem like we've found a maximum flow. But we don't yet know that it's always the case, that just because there are no augmenting paths, I'll draw a little diagram to explain the reasoning I'm using here. Just because I don't have any augmenting paths doesn't mean, so it doesn't necessarily mean that I'm looking at a maximum flow. I have yet to prove that. I'm going to prove that in a minute, but there's no requirement that just because there are no augmenting paths that means I have a maximum flow. Because for all I know, maybe there's some other way of improving the flow that doesn't involve augmenting paths. So I am not claiming that. What I'm claiming is the converse. I'm claiming this. So if I have a maximum flow, then certainly there can't be any augmenting paths. That's all I'm saying. So I have a maximum flow, there are no augmenting paths. That's the only property I'm currently using at this stage in the proof. All right, so there are no augmenting paths. That means if I do a traversal of the residual network GF, starting at vertex S, the source vertex, there is no way that I'm going to reach vertex T, because if I could do that, I would have an augmenting path. Okay, fair enough. Let's do that traversal and figure out which vertices I can reach in my residual network. Okay, so I do a traversal starting at vertex S. There are no augmenting paths, so I never get to vertex T, but I do reach some other vertices in the meantime. Let's call that collection of vertices, everything reachable from vertex S, let's call that the set uppercase S. And similarly, let's define all of the remaining vertices to be called T. Maybe you can see what I'm doing here. I'm clearly playing at defining an ST cut. So since no augmenting path exists, we know that our sinc vertex is in the set T. And we also know, of course, that because of the way we define the set S, that our source vertex is in S. And certainly that because of how we defined T, every vertex of the graph is in exactly one of S or T. And therefore, I'm going to claim that ST is an ST cut. Now, if we think about how the Ford-Fulkerson algorithm actually does this, suppose that I use a basic traversal to find augmenting paths. Okay, the way that works is I go to my residual network, I start at vertex S, and I perform some traversal. So let's say I use BFS or DFS. So I go up to vertex V1, and then I get stuck. I can't go any further because all of the edges, all of the other neighbors to V1 are inbound neighbors. So I back up, I go up to vertex V2, I go from there to vertex V5, and that's it. So I was only able to reach this collection of vertices. Okay, so what I've done in the proof is I've said, let's call that the set S. All of the vertices currently reachable from S in the residual network, we're going to call that the set S. Because there are no augmenting paths, there is no way to reach T, and so the vertex T will never be in this set. Now I just want to illustrate a couple of sort of obvious insights. Like once you see them, I think they'll be pretty clear why they hold, because we know enough about how the Ford-Fulkerson algorithm works. One other thing I want to observe here is that I have a maximum flow F. So I started my proof by saying, consider a maximum flow F. And then I say, let's see what the Ford-Fulkerson algorithm would do if I try running it for one iteration on this maximum flow. I'm not claiming that I use the Ford-Fulkerson algorithm to compute the maximum flow. Because if I were claiming that, I'd be in trouble, because I haven't proved that it does. I don't know that it produces a maximum flow. Instead, I'm saying, let's consider a maximum flow and see what happens if I run the Ford-Fulkerson algorithm for one more step on that. Okay, so I've defined my set S to be all of the things reachable from the source vertex in the residual network. The first insight behind the proof is that if I look at any edges entering the set S, all of those edges must have zero flow. So any edge pointing into my set S must have zero flow over the edge. This must be something like 0/10. Now that seems like a weird assertion to make out of nowhere, but once you think about it, it's pretty clear that it has to hold. Because suppose there were some flow along this edge here. There were some flow from U or from V to U. Well, what that means is when I go looking for augmenting paths, once I get to vertex U, I would be allowed to travel along the edge UV. Because, of course, since there's flow from V to U, I'm allowed to return that flow to sender. I'm allowed to send it backwards. And that means that I could get to vertex V, which in turn means that vertex V should have been included in S. but vertex v wasn't in S, so that would be a contradiction. And so what that tells us is there cannot be any flow across the edge VU, because if there was, v would be an element of S, and we've just defined that it isn't an element of S. Okay, so insight 1 is that for all of the edges pointing into my set S, there must be zero flow along those edges. Insight 2 is pretty much the same property but flipped around. So for all edges that leave the set S, so where the vertex U is in S and the vertex V is in T, those edges must all be saturated. So in other words, this edge here must have 5 out of 5 or something. And the justification is pretty similar. So suppose that this edge wasn't saturated, it has 5 out of 10. Well, if the edge has 5 out of 10, then when I go looking for augmenting paths, I would have been able to get all the way to vertex V. Vertex V would have been reachable from vertex S in the residual network. And if that were the case, then vertex V would be in S, which is a contradiction because I just said a minute ago that vertex V wasn't in S. And that's enough to give us what we need for insight 2. And it actually turns out that once we have insight 1 and insight 2, the proof of the max flow min cut theorem, which as I said a minute ago was the most profound theorem we're going to see in the course, the proof of that theorem isn't that tough. All I really have to do is chase some definitions. So what I want to show is that the value of the flow F, which I defined earlier to be a maximum flow, is equal to the capacity of a minimum cut. And what I'm going to do basically is show that it's the capacity of the specific cut that I defined. By weak duality, if I can find a cut whose capacity is equal to the value of my maximum flow, automatically this has to be a minimum cut. Okay, so to show that, I've defined my cut ST, so I've defined my set S and my set T based on what the Ford-Fulkerson algorithm would do. All I really have to do is apply a bunch of definitions in sequence here. So we already know that the value of any flow F is equal to the flow across any particular valid cut. So I have a cut, ST, which means that the value of my flow F is equal to F of ST, the flow across the cut. And so here's a slide you can consult if you don't believe me on that. I've also already defined this is just the definition of the amount of flow across a cut, the total amount of flow leaving S minus the total amount of flow entering S. That's a definition from slide number 19. Okay, so by insight 1, all of the edges entering S have zero flow, which means this summation can be turned into this. I'm just adding up a bunch of zeros. Okay, so that's one option. I'll just leave this as a sum of zeros for a minute. Insight 2 tells me that all of the edges leaving my set S must be saturated. That is, for all of those edges, I must have it be the case that F of UV is equal to the capacity. The edge is saturated, so the flow across the edge equals the capacity. What that tells me is that this sum here of the flow values of those edges just equals this sum here of the capacities of those edges. And now all I have to do is clean it up. So I've reduced the value of F is actually going to be equal to this. And of course, the sum of all zeros, I can just wipe that out. And so I end up with this term here. And recall that this is just the expression for the capacity of a cut. This is the definition of what the capacity of a cut is. And so I've now shown that the value of my maximum flow is equal to the capacity of this cut, which I was able to explicitly construct. In fact, the Ford-Fulkerson algorithm sort of handed it to me. It's just all the vertices that it visits looking for an augmenting path on the one hand, and all the vertices that it doesn't visit because they're unreachable on the other. And that's the max flow min cut theorem. And here's where the slides say what I said earlier, which is that the max flow min cut theorem is a really big deal. Not only does it give us a way of asserting that a flow is maximum, I just have to go find a cut whose capacity matches the value, it actually also does something a lot more profound. It is able to relate two apparently quite different problems and make them basically two sides of the same coin. What it's really doing is telling us that the maximum flow problem is the dual of the minimum cut problem. In other words, any solution to the maximum flow problem implies a solution to the minimum cut problem. If you have a maximum flow, then by the logic I just gave in that proof, I could construct a minimum cut. And it turns out if you have a minimum cut, you can construct a maximum flow. Solving one problem provides a solution to the other. Even though the problems themselves are quite separate, this property of duality that is codified by the max flow min cut theorem inextricably relates both problems together. That is a really big deal, especially also because we've related a maximization problem on the one hand to a minimization problem on the other. And a nice bonus that falls out of our proof, even though the proof itself is pretty profound given what it's proving, A nice bonus that falls out of it is that it actually also proves the correctness of the Ford-Fulkerson algorithm. Because what it shows us is that if we ever reach the case where the Ford-Fulkerson algorithm can terminate, and remember that the algorithm terminates when there are no augmenting paths. Well, if there are no augmenting paths, that means we're in a situation that the set of vertices reachable from S doesn't include the vertex T. And by the construction that we gave in the proof, we can construct a cut at that point, which is guaranteed to be valid because T will be in the set T and S will be in the set S. We can construct a cut whose capacity equals the value of the flow at that point, which is showing us that when the Ford-Fulkerson algorithm terminates, it does indeed have a maximum flow. So the algorithm, therefore, is correct. So we've managed to take care of two things, defining a maximum flow and verifying that a maximum flow is correct, having conditions for that, and showing that the Ford-Fulkerson algorithm actually computes a maximum flow. That said, I've got a bit of a disclaimer here because, wait a minute, at the end of the previous lecture, didn't I make a point near the end there that the Ford-Fulkerson algorithm may not terminate in some cases? Wouldn't that be sort of a fatal error? Now actually, on the one hand, we don't have to worry about that in our context because I observed that that's only ever going to happen if the capacities of some edges are arbitrary irrational numbers. So we'll pick our favorite irrational numbers here. There's pi, there's e. I guess something ought to be the square root of 2 here. So let's do 1 over the square root of 2. There we go. So if the edge capacities are truly irrational numbers, not just rational approximations of them, but actual irrational numbers, which are rather difficult to fully represent in a computer, although there are ways of doing it basically symbolically. I noted that in those cases, it's possible that the Ford-Fulkerson algorithm isn't actually ever going to reach the termination condition. It's going to keep performing augmentations forever, each one getting smaller and smaller and smaller. It's going to basically asymptotically approach a maximum flow rather than finding one. You might say, wait a minute, wouldn't that jeopardize the proof I just wrote? Didn't the proof hinge on how the algorithm works? It actually turns out that it doesn't hinge on that the proof is still fine even if there are cases where the algorithm doesn't terminate. Because you will notice that at no point during the proof did I run the algorithm to find the maximum flow. That's why midway through the proof I backed up and made extra sure that I clarified that point. All I did was I said, here's a maximum flow. What would the algorithm do at this step? And one way or another, if the flow is maximum, the algorithm would terminate. It's only the process of getting to the maximum flow that causes the algorithm to enter an infinite loop in some cases. So my proof is still valid, even if there are cases where the algorithm doesn't terminate, because my proof doesn't require that the algorithm was run from the beginning. It just requires that if I have a maximum flow, that I look at the vertices that are reachable in my residual network GF. So that's why the proof isn't jeopardized by that. Actually, even if it were jeopardized by that, which it isn't, I have another way around the problem, which is that we're going to show in a few minutes that there is an algorithm that is a variant of the Ford-Fulkerson algorithm. It's similar enough that I could still have used that algorithm in my proof, and the algorithm we're going to see in a few minutes does always terminate. So not only does it terminate, it turns out it also has a nice fast running time. So if I had wanted to present that algorithm first, then I wouldn't have had to give this disclaimer a minute ago because there wouldn't be the case where the algorithm doesn't terminate. And I'm sure you're thinking, well then why didn't you do that? Why did you just spend 5 minutes justifying yourself when you could have just done this in a different order? And we'll see why when we get there. But basically it's because if I'm going to do two proofs in this lecture, I wanted to do the max flow min cut theorem first because the second proof in this lecture is sort of exhausting. So I guess that takes us right to the algorithm that I want to discuss next, which is we've shown that with the Ford-Fulkerson algorithm, I can compute a maximum flow, and that is under the restriction that we've adopted where the capacities of every edge are rational, or in the context of this course where they're all integers, we can compute maximum flows in this amount of time. So the number of edges multiplied by the value of the flow. And we now know that the flow produced truly is a maximum flow. So we can now begin saying the number of edges multiplied by the value of a maximum flow. As I mentioned a few times recently, including at the beginning of this lecture, a running time that depends on a property of the output is a bit scary because we don't know in advance how long the algorithm is going to take because we don't know the value of this parameter until the algorithm is finished computing it. And moreover, even if we do know the value of that parameter, we can imagine lots of cases, and as an exercise on the side, see if you can create one right now, we can imagine lots of cases where the value of a maximum flow is way larger than the size of my input. It could be exponentially larger, which means that this algorithm, the basic Ford-Fulkerson algorithm, is not polynomial in my input size. Now, as I said earlier, the fact that it's not polynomial isn't the biggest problem. There are algorithms out there that aren't polynomial. That's sort of too bad, but not the end of the world. I would argue that really the fact that the running time isn't easily parameterized by something you know in advance, that actually might be scarier because you have no real assurance of how long things are going to take. Now, there actually are a variety of different algorithms that can compute maximum flows in polynomial time, some of which are similar to the Ford-Fulkerson algorithm and some of which aren't. Now, the goal of covering flows in this course isn't to give a survey of all of those things. It is, however, important, among other reasons so that we can go put out that fire with pride, it is important that we show at least one polynomial time algorithm to solve the maximum flow problem. And the one we're going to cover, which I think is sort of the most popular one, at least from the algorithm course point of view, the one we're going to cover is actually a really tiny modification of the basic Ford-Fulkerson algorithm. There are plenty of other ones, though, and some of them might actually be better for certain reasons. So one of the reasons I'm covering the one that we're going to cover is because, well, first, it seems to be the one that everybody covers, to the point that it's been hard-coded into the syllabus of this course. That's a pretty pragmatic reason to do it. And also because it's such a small variation on the Ford-Fulkerson algorithm that it's pretty easy to justify, although the proof is going to be quite exhausting. And the algorithm is called the Edmonds-Karp algorithm. We'll just take a minute to take it in. Notice that it is basically line for line identical to the Ford-Fulkerson algorithm on the previous slide. There's only really one difference, and that's line 4. The only difference between the Ford-Fulkerson algorithm and the Edmonds-Karp algorithm is that the Edmonds-Karp algorithm requires that you always use BFS to find your augmenting paths. That's literally it. So all this time, the only reason that the Ford-Fulkerson algorithm was taking so long was that we weren't using BFS. We could have been using some other traversal. We could have used DFS or some other arbitrary traversal mechanism, and that wouldn't have been enough to guarantee polynomial time. Turns out if you always use BFS, you will get a polynomial time algorithm. And so one observation we can make right off the bat, based on what we know about BFS, is that if we use BFS to find augmenting paths, the augmenting path we find at each step is the shortest augmenting path possible in terms of the total number of edges used. You recall that I made a big deal about when we should use the term shortest path or not a few lectures ago. Part of it was seeing in advance that I would need to use that term here. So of course, BFS, when you compute a BFS tree rooted at a particular vertex U, the paths in that BFS tree to other vertices V are guaranteed to have the fewest number of edges among all possible UV paths in the graph. Now, the Edmonds-Karp algorithm is named after Edmonds and Karp, and they published the algorithm jointly. So there's no need to argue about whether we should call it the Edmonds algorithm or the Karp algorithm. They wrote one paper together. So pretty clearly that as far as the two of them are concerned, they can share joint credit. Their publication was in 1972. Now, there is one special case I have to describe, though, which is that it was very similar. What Edmonds and Karp described was pretty much the same algorithm as something that was published earlier by Dinitz in 1970. And so we should ask ourselves the question, why am I not calling it the Dinitz Edmonds-Karp algorithm? And I thought a lot about this, as I've done in previous lectures. It's important to me that I get the names right. And basically, I came down on the side of still calling it the Edmonds-Karp algorithm, because although Dinitz was, I guess, the originator of this idea, Dinitz was the first person to invent the idea of using BFS as a way of making the algorithm polynomial time. The technique Dinitz used was a little bit different, and the running time Dinitz proved was actually faster. The proof I'm going to show you in a few minutes of the Edmonds-Karp algorithm is based on the running times given by Edmonds and Karp. And so because the algorithms have different running times, they are, I guess, going to be distinct algorithms. I used a similar argument when we talked about the all pairs minimum cost path problem, about whether or not to credit one person alongside of Floyd, Warshall, and Roy. So we should give Dinitz credit for being the first person to publish this style of algorithm with a polynomial running time, but the one I'm covering is the one by Edmonds and Karp. And so the key insight all three of them had wasn't the idea of using BFS, just to be clear. I mean, obviously, adding this line that says, please use BFS, isn't really enough to say that you've invented something new. The contribution that all of them made was proving that if I do this, I get a polynomial running time. So the algorithm itself, the specific steps I take, that wasn't the insight that they provided. It was finding a way of proving that if I always use BFS, I'm guaranteed to have polynomial running time. And that was enough that even though the change was pretty minor from the original Ford-Fulkerson algorithm, we still call the result the Edmonds-Karp algorithm, to acknowledge that if it weren't for the proof that they wrote that it was polynomial, we wouldn't have used this restriction of requiring BFS. Okay, so I mentioned earlier that the max flow min cut theorem, in my opinion, is the most powerful and profound theorem of the course. It is a really big deal, to the point that I feel bad about how I can't show off what a big deal it is. It's just hard to show applications that really emphasize what a big deal it is right now. Now, the Edmonds-Karp algorithm is a big deal, but not nearly as big of a deal as the max flow min cut theorem. In fact, I would argue that in terms of the overall significance of the algorithm, certainly the original Ford-Fulkerson algorithm is more of a big deal than Edmonds-Karp. Edmonds-Karp is still very important because it shows us a polynomial time way of solving the problem. That all said, the proof that the Edmonds-Karp algorithm is polynomial is going to be the most complicated proof of the course, by far. So we're at slide 67. The proof is going to take us through, I think, slide 115. We're going to have to spend the next 40 slides on this proof. It is a lot. It is not the kind of thing that I expect anybody could digest by watching a lecture. So despite my best efforts of drawing the pieces of the proof on these slides and my best effort to explain them in this video, there is pretty much no way that I can expect anybody to have wrapped their head around this proof in one watching. The only way I think you can understand this is by, ideally the lecture helps a bit, but probably you're going to have to go back through the slides and just try out the steps of the proof yourself to put the pieces together. There are lots of pieces, many of which are rather tedious. Putting them together isn't really the easiest thing in the world, even if I illustrate what I'm doing, especially because I can only put so much information on a slide at a time. So to do that, I have expanded the proof out a lot. I've tried to include some examples, and I'm going to begin, before we do the proof itself, by describing the overarching insights of the proof. So the proof is going to rely on 3 facts about the augmenting paths found during the Edmonds-Karp algorithm. These are paths that have been found by BFS. And the idea behind these 3 facts is that if we take them all together, they allow us to bound the maximum number of augmenting paths we need to find before we hit a maximum flow. They allow us to bound the total number of augmentations needed in the worst case. Before I talk about those facts, I have to recall some notation. So recall from, way back in like lecture 25 or 26 or something, that the distance in any directed graph, this is not a definition specific to flow networks, the distance from vertex u to vertex v is the minimum number of edges in any path from u to v in G. It is the length of a minimum length path from u to v. Also recall that back when we talked about BFS, we proved this, that a particular UV path produced by running BFS starting at vertex U, so if I generate a BFS tree rooted at vertex U, and I find a path in that tree to a particular vertex V, it is guaranteed that the length of this path will be d of UV. That is, this will be a shortest path with respect to the number of edges in the path from vertex U to vertex V. And that applies whenever I run BFS starting at vertex U. Okay, I want to generalize that notation a little bit because we want to talk about augmenting paths. And we know that augmenting paths aren't just arbitrary paths in the graph, they're paths along edges that have some residual capacity, so non-zero residual capacity. And of course, to know the residual capacity, you have to know a particular flow for our flow network. Okay, so for a particular flow f, let's define df of uv to be the distance from u to v in the residual network gf. So remember that if I can get from, let's say, the starting vertex S, the source vertex, to a particular vertex V, that means there is some way to push flow from S to V. If there's a path in my residual network GF from S to V, there is some way I could push flow from S to V. And of course, that means if I can find a path from S to T in my residual network GF, that corresponds to an augmenting path in my original graph. So you could also define, if you don't want to talk about residual networks, you could also define df of uv to be the distance from u to v in the original network G along edges where there is a non-zero residual capacity, where there is some ability to push extra flow along the edge. Okay, so here are the facts that we are going to leverage in the proof that the Edmonds-Karp algorithm is polynomial. First one, fact 1. The distance with respect to a particular flow, so if I look at the state of the flow as the algorithm progresses, so of course at each step of the algorithm I perform an augmentation, I increase the value of my flow. If I pick some vertex, let's do vertex v1, if I pick any vertex, the distance of that vertex in the residual network, the value of df, over the course of the Edmonds-Karp algorithm, the distance of any vertex v from the source vertex s will never decrease. It might stay the same between two iterations, but it will never go down. I can quickly map out what that means. I'm going to come back to this example later. But if I look at, in this graph here, if I look at augmenting paths, the first one I choose in the Edmonds-Karp algorithm would be this relatively direct augmenting path from S to T. Once I'm done the augmentation, I end up with this. So I've got 5 along this edge, 5 along this edge, 5 along this edge. Before I did the augmentation, the distance from S to V1 was 1. I could get from S to V1 directly via one edge. After the augmentation, there is no residual capacity along the edge SV1, but I can still get from S to V1 in the residual network. So for example, this is not the only way of doing it, but I could go all the way like this. I could go from S to V7 to V8 to V9 to V10 to V11 to V1. Notice that the distance from S to V1 went up. Because this edge got saturated, I can no longer get there directly. What fact 1 is saying, what we're going to prove in a few minutes, is that the distance of any vertex from the source over the course of the Edmonds-Karp algorithm never decreases. It might go up, it might stay the same, but it never decreases. Fact 2. Fact 2 is actually a bit easier. Fact 2 says that on every augmenting path, there is at least one edge such that at the end of the augmentation, the residual capacity of that edge equals 0. This is actually a consequence of the way that we defined augmenting paths originally, or the way that we defined the augmentation process. So just to remind you why this is the case, if I consider a particular augmenting path, so there's S and there's T, and here's some edge in the middle. Suppose I have this set of capacities. There's 0 out of 5 on this, there's 0 out of 5 on this, and this edge has 0 out of 2. So the total amount of flow I can push along this path is obviously 2 units, because that'll max out this middle edge. And in general, along any augmenting path, there will always be one edge that gets maxed out in some sense as a result of the augmentation. Once I've maxed it out, the residual capacity from this vertex U to this vertex V has to be 0, because I can't transport any flow along this edge anymore. Now, with augmenting paths, remember that there is this bidirectional aspect where flow can be pushed in either direction. So I could also have this situation here where this edge currently has, let's say it has 2 units out of 5 being pushed from V to U. This is an augmenting path still. I can still go from S to T because I can push flow backwards along the edge VU. But notice that if I do that, the capacity of the path is 2. Once I've pushed 2 units along the path, this edge has 2, this edge now has 0, and then this edge has 2. Notice that that means the residual capacity from U to V is also going to be 0. So in any event, no matter how I create my augmenting path, if it is an augmenting path, after I perform an augmentation, at least one edge along the path will have no residual capacity left. I will have maxed out its residual capacity. Okay, fact 3. Although it is the case that a particular edge E might appear in multiple augmenting paths over the course of an algorithm, so over the full run of my Edmonds-Karp algorithm, a particular edge could show up over and over again. Now, in some of the iterations where it shows up, it might not be fully saturated. That is, I can envisage a case where, not in this graph here, but for example, suppose that this edge has a capacity 2. This edge might end up getting used in an augmenting path and it doesn't get maxed out. That could happen. And fact 3 doesn't really care so much about those cases. Fact 3 considers cases where the edge does get maxed out. So for example, if this edge here gets 5 out of 5, that would be an iteration where the edge is fully saturated. If on some future iteration I push flow backwards from V2 to V1 and it ends up at 0 out of 5, that's a case where this edge got fully depleted. And so fact 3 is that although a particular edge might show up over and over again in augmenting paths, each time the edge is fully saturated or fully depleted, it has to be further away from the source vertex than it was the last time that happened. Now that's a very weird abstract statement. I have an example to try and illustrate that. Okay, so before we get into the proof itself, because the proof itself has lots of moving parts, I want to use this network to give an example to sort of show off what makes the Edmonds-Karp algorithm special and how those three facts factor in. So, over the course of the run of the algorithm, keep an eye on edge v1, v2. I'm also going to watch the vertex v1. I want to observe that as the algorithm progresses, the distance among edges with residual capacity greater than 0, the distance from S to v1 is going to go up. And that the distance from vertex S to this edge along augmenting paths is also going to go up. So every time this edge gets fully saturated or depleted in an augmenting path, it is further away from S along that path than it was the last time that happened. Now, remember, of course, that because I'm using BFS to find augmenting paths, the augmenting path chosen at each step is the shortest path from S to T. So the first augmenting path oh wait, we're not there yet. So at the beginning of the algorithm, before I've pushed any flow at all, we have the all zero flow, and the distance from S to V1 is 1, because I can reach V1 directly along this edge, which does have residual capacity. Okay, so the very first augmenting path is this one, this very direct path from S to T. And by using this path, I'm able to push 5 units of flow. And so notice that this edge, among others, this is not the only edge to which this applies, but certainly the edge V1, V2 is now saturated. The question is, can I still get to V1 from S? And the answer is yes in 2 ways. So I can still reach V1 from S in the residual network. I could either go all the way around and get to V1 along the outside, but I could actually also go down to V3, over to V4, up to V2, and then backwards to V1 along the edge V1, V2, because I can always return these 5 units of flow to sender. So after the augmentation, the distance with respect to the current flow from S to V1 is 4, because the shortest path from S to V1 in the residual network, the shortest potential augmenting path from S to V1, actually goes backwards along the edge V2, V1. Now I know talking about shortest paths and then traveling along edges backwards might seem confusing. Remember that if I use the residual network directly, so here's the residual network, with this flow that I have at the end of the previous iteration, in the residual network, there will be an edge from V2 to V1, and we can see that. Notice that in the residual network, the distance from S to V1 is 4 at this step. Okay, so the next augmenting path is actually this one. So the path S to V3 to V4 to V2 to V1 to V5 to V6 to T. And we can observe that that is definitely shorter than the alternative. The other augmenting path I could try would be the one that goes all the way through the graph, which is pretty clearly pretty long. Okay, so I perform this augmentation. Now, notice that as part of the augmentation, I am pushing flow backwards from V2 to V1. So whereas previously this edge was saturated, the last augmenting path saturated this edge, this augmenting path fully depletes that edge. And so notice that afterwards there actually is going to be more residual capacity from V1 to V2, whereas previously at the end of the last iteration there was no residual capacity from V1 to V2. At the end of this next iteration, by clearing out that edge, I can now transport more flow from V1 to V2. Now also notice that in the previous augmenting path, the edge V1, V2 was 1 edge away from S. So the previous augmenting path was this, and so the edge V1, V2 was 1 step away from S. At this augmenting path, the edge V1, V2 is quite a ways away, so 1, 2, 3 steps until I get to either endpoint of the edge. And that's fact 3 from earlier. So fact 3 says that any edge that appears that is fully saturated or depleted multiple times during the algorithm, any edge with that property is going to be further away from S every time that happens. Only when it's saturated or depleted. It could appear on augmenting paths for other reasons in the meantime, but every time it is fully saturated or fully depleted, it is further away from S along the augmenting path it appears on than it was last time that happened. Okay, so after that augmentation, so after I do this one here, the distance with respect to the current flow from S to V1 is now 6, because I can't travel this way, I can't travel this way, but I can still reach V1 by going all the way around, and that's a path of length 6. If I look at the residual network, there it is. So in the residual network, there's no way to go from S to V1 directly, there's no way to go from S to V3 directly, but I can walk all the way around the outside on this path of length 6 to reach V1. The next augmenting path is actually this huge path here. I walk all the way around the outside of the graph from S to V7 to V8 to V9 to V10 to V11 to V1, across the edge V1, V2 again, down to V12 to V13, 14, 15, 16, and down to T. And notice that this augmenting path again saturates the edge V1, V2. So over the course of the algorithm, this edge, V1, V2, has been saturated, then depleted, then saturated again, which provides ample evidence that a single edge can appear over and over again in augmenting paths. Notice that this time the edge V1, V2 appears, it is even further away from S than it was the last time. The first time, the edge was 1 step away from S. The second time, the edge was 3 steps away from S until I got to either endpoint. And the third time, it is 1, 2, 3, 4, 5, 6 steps away from S. Now, as it turns out, at this step, we're done. We now actually have a maximum flow. We have the tools to verify that now because we know about minimum cuts. So the flow that I have currently has value 15. If I choose the vertex S as the entire contents of the set S of one side of the cut, which is what I would do with the Ford-Fulkerson algorithm, because if I look at all the vertices that are reachable from S in the residual network, because these 3 edges are saturated, all I can reach is the vertex S. We can observe that indeed this cut has capacity 15. So because I have a cut with capacity 15 and a flow with value 15, I know the flow is maximum and the cut is minimum. Okay, so that was an illustration of the facts I want to demonstrate. Over the course of the algorithm, the distance of any vertex from the source vertex will never decrease if I'm only traveling along edges with residual capacity, or thinking about the distance in the residual network. Fact 2 is on every augmenting path, at least one edge, not necessarily just one edge, but at least one edge needs to be fully saturated or fully depleted. In other words, all of its residual capacity will be gone after the augmentation. And finally, fact 3 says that a particular edge might show up more than once in augmenting paths. However, every time it is fully saturated or fully depleted, it is further away from the source vertex along the path than it was the last time it was fully saturated or fully depleted. Now, how do these things prove that the algorithm is polynomial? So basically, if we can prove fact 2 and fact 3, we can argue that each edge can be saturated or depleted at most this number of times. So the idea is if every time an edge is saturated or depleted, it has to get further and further away from the source vertex, well, there is a sort of maximum distance. I mean, we could have an edge that's 1 step away from the source vertex. I guess we could even have an edge that's 0 steps away from the source vertex. But if the next time that I fully saturate or deplete it, it's a little bit further away, and it's further away the next time after that, and the next time after that, well, there is only a certain number of steps away it can get, and it can never get any further away than that, because we know that our augmenting paths, the maximum length of an augmenting path is this, because this is the maximum length of any path in the graph. So what we can argue is that if we have basically just fact 3, so fact 2 is going to come into this in a minute. If we have fact 3, we can argue that each edge can be saturated or depleted at most this number of times. It's actually a little bit less than that, but certainly at most this number of times. Because if it has to get further away at every time it's saturated or depleted, there's only so far it can get before you're out of options, before there's no way of pushing it any further away. So the maximum length of a path is the number of vertices, give or take, and so the maximum number of times I can saturate or deplete an edge is also that number. Now, if I know that every edge can be saturated or depleted at most this number of times, then the total number of augmentations actually has to be at most this, and there is where fact 2 comes in. So fact 2 tells me that for every augmenting path, at least one edge has to be fully saturated or depleted. But we know that each edge can be saturated or depleted at most this number of times. So in the worst possible case, where every single edge gets saturated or depleted the maximum number of times, the number of augmenting paths, it can be at most this. Because for every augmenting path, we must saturate or deplete at least one edge. Okay, so if I show that at most this number of augmentations is necessary, that's actually enough to conclude that the whole algorithm is polynomial. Although when the time comes, in a while, I will formally prove that. So I can't just say that now. I will actually fully prove that when the time comes. In the meantime, I have to prove facts 2 and 3. Notice that for the final justification, to actually get to this number, all I really need is fact 2 and fact 3. I need fact 3 to show me that each edge can be saturated or depleted a maximum number of times. I need fact 2 to tell me that every augmentation must involve one edge being saturated or depleted. So where does fact 1 come into all of this? Well, fact 2 is easy to prove on its own. In fact, we're not even going to bother proving a lemma for fact 2, because fact 2 follows from the definition of the residual capacity of a path, because we saw that the capacity of a particular path is just the minimum of the capacity of some edge along that path. So the capacity of the residual capacity of uv, where uv is an edge along the path p. So we know that fact 2 has to hold, because there's going to be at least one edge on the path whose capacity is equal to the capacity of the path, so that after the augmentation, there's no capacity left. Now, as far as fact 3 is concerned, that's where I need fact 1. In order to write the proof of fact 3, I need to have fact 1 already proven. Well, there might be some other way of doing it, but proving fact 1 first seems to be the easiest path I have to proving fact 3. Okay, so it's time to actually write the formal proof. I'm going to state these things in terms of some lemmas and then bring them together. So fact 1 is going to become something I'm going to call lemma A. And fact 3 is going to become something I call lemma B. I'm not going to bother with giving fact 2 a name because, as I said a minute ago, it's a consequence of a definition. Now, the proofs I'm going to present and the breakdown of the proof are not my own. So whereas sometimes I soldier ahead and try and come up with my own proofs to things, I have not done that here because this is not an easy proof to write. And while I might be able to muddle my way through writing a proof of this from scratch, I don't think that the result would be elegant enough to give a lecture on. So I'm going to leave this one to the writers of the CLRS book, who have written a very nice, elegant, and compact proof. So the proof that I'm expanding on the following slides is not my original work. It is adapted from CLRS. Now, some of the adaptations are significant, so I've changed a bit of notation and I've broken the proof into different pieces to fit it on slides. So of course it's my fault if I've made the proof wrong by doing that, but ultimately the key insights of the proof are all based on the CLRS book. Okay, so lemma A. Now, lemma A is a formalization of fact 1. So fact 1 is the statement that the minimum distance, that's actually that's not necessary, that's redundant, the distance of each vertex V from the source vertex S in the residual network never decreases as the algorithm proceeds. Now, I have to write that out formally. So the way I'm going to phrase the lemma is, okay, so the algorithm, the Edmonds-Karp algorithm, goes through a sequence of different flows. It starts from a zero flow, then it performs a bunch of augmentations. So let's call the flow I start with, the all zero flow, we'll call that F0. Let's then say that after I performed one augmentation, the flow I get is called F1. And then after two augmentations, I get F2. Each augmentation corresponds to one iteration of the outer loop of the algorithm. So what we'll do is define Fi to be the state of the flow at the end of iteration I. Now I highlight that because the notation we have to use is a little bit clunky here, because at the end of iteration I is after I've done the augmentation for iteration I, which means the augmenting path that I find for iteration I will actually be an augmenting path in based on the flow I had at the end of the previous iteration. So the residual network I'm looking in to find an augmenting path at iteration I is this residual network. I'm using the flow that I had at the end of the previous iteration and finding an augmenting path with respect to that. Okay, so with that way of numbering our flows, lemma A states that for every vertex in the graph, the distance of a particular vertex with respect to a flow, the distance of vertex V at step I minus 1 is less than or equal to the distance of vertex V at the end of step I for all iterations. The proof is by contradiction. This is one of those proofs where, having fully written it up, I wondered whether it really needed a contradiction, whether we couldn't just prove it straightforwardly. However, the proof is complicated enough that I will take the contradiction method if I can use it. So using a proof by contradiction will allow us to discard a couple of cases early, because if we can find any contradiction, we can just elide that case altogether. So I'm going to stick with the proof by contradiction. Okay, so I'm going to suppose that the distance of some vertex from the source does decrease. So I'm going to suppose that the theorem is false. Now, what's difficult about this part of the proof is that I actually have to really narrow things down to make this feasible, to make this doable. Notice how I say, suppose that the distance of some vertex decreases at some iteration. What this is alluding to, in a sense, is that if the theorem is false, so if we're doing a proof by contradiction and we suppose that the theorem is false, we don't know that only one vertex has this problem. Maybe a whole bunch of vertices have their distances decrease. I can give a pretty easy example of how that pretty much has to be the case for a lot of graphs. Suppose I have this state here where I've got a bunch of vertices. Suppose I have this vertex u here. And suppose that vertex u has its distance decrease at a particular iteration of the algorithm. But now suppose that vertex u has some outbound neighbor w. Wouldn't it be true that if the distance from S to U decreases, that it's quite possible that the distance from S to W decreases as well? I would say that's likely. So to be careful in my proof, I have to very carefully define the specific vertex I want to talk about. I want to basically show that for some vertex V, whose distance decreases, there is no way for that to happen that doesn't result in a contradiction. To make that doable, though, I have to be very careful how I define V. Okay, so because multiple vertices could have their distance decrease, for all I know, and this could happen at lots of different iterations of the algorithm, I want to very carefully define the specific case I want to talk about. Okay, so let I be the earliest iteration where the distance of some vertex decreases. Okay, so it could be the case that at iteration I, a whole bunch of vertices have their distance decrease. So to narrow things down further, let's define a set di consisting of all vertices whose distance decreased at iteration I. So the set di is all vertices q such that the distance from S to q at iteration I minus 1 is greater than the distance at the end of iteration I. So all the vertices whose distance decreased during iteration I. I want to talk about one specific vertex V. So define V to be the element of di with the minimum value of distance from S. So there could be lots of different vertices in di with different distances from S. Define V to be one such vertex, but with the minimum distance from S. Now, I guess there could even be a bunch of vertices in di that are tied for that. I don't care which one you choose in that case. All I care about is there is no vertex whose distance changed that has a lower distance from S than vertex V. Okay, so I know that's a tough one. I'm going to have to come back to that a couple of times. We're going to see where I'm able to use all of this, this careful selection of V, where all this bookkeeping is going to be useful. Okay, so let's take a look at the state of the residual network after iteration I. Now on the diagrams coming up, I'm going to keep flipping back and forth between the state of the residual network after iteration I and the state of the residual network during iteration I, or you could also frame that as being after iteration I minus 1. Okay, so I'll label which state I'm working with this little thing up at the top corner. Okay, so let's find a minimum length path from S to V in the residual network after step I. So after I perform the augmentation at step I, that is the step where the distance decreased. Consider a minimum length path from S to V in that residual network. We know that the length of that path will be will be d of Fi of S to V. Okay, so one thing I can observe, the proof doesn't write this explicitly, but I think it's reasonable that we can conclude this, is that the vertex V is obviously not equal to the vertex S. That would be impossible. What do we know about the vertex V? We know that its distance from S decreased. Now, if V were equal to S, that's completely impossible. The distance from S to itself is 0. There's no way that the distance of any vertex to itself could ever be -1. Okay, so that means that the vertex V is not equal to the vertex S. Why do I care about that? Because that means that the path P contains at least one edge. So it's reasonable to talk about the predecessor of the vertex V along the path. So let U be the vertex that precedes the vertex V along the path P. Remember that P is a minimum length path from S to V. So U is the vertex on that path right before V. And we know that such a vertex must exist because the length of the path has to be at least 1. We also know that the distance from S to U has to be the distance from S to V, all minus 1. And we actually know this by a result that we proved a while ago. The reason that we know this is because the path P is a minimum length path from S to V, which means the part of that path that goes from S to U must be a minimum length path from S to U. In fact, this is actually just the subpath lemma from when we talked about minimum cost paths. We could argue it's a special case of it, or we could argue that the version of the subpath lemma that we proved earlier was a generalization of a more fundamental subpath lemma that applies to all graphs. So in any graph, even a non-edge weighted graph, it is the case that if you have a shortest path from S to V, and the vertex U appears along that path, the portion of the path from S to U must be a shortest path from S to U. If you want a full proof of that, just go look at the proof of our subpath lemma from when we studied minimum cost paths. Okay, so what we now know is that the distance in the residual network after iteration I from S to U is equal to the distance from S to V, all minus 1. Okay, so hold that thought. Okay, so another claim I want to make is that the distance from S to U did not decrease during iteration I. That is, the distance at iteration I minus 1 might have been smaller than the distance at iteration I, but there is no way that the distance was larger. And this is where my careful definition of V is going to come in handy. So my claim is that the distance from S to U did not go down between iteration I minus 1 and iteration I. And my justification that is that if it did, so if the distance did go down, well, remember that I defined this set a few slides ago, this set di of all the vertices whose distance went down during that iteration. If the distance to vertex u went down, then vertex u is a member of this set. Also remember that I chose vertex v to be the element of di with the minimum distance. So if we go back over to where we were, if vertex u had its distance decrease, then vertex u was in di. Additionally, a minute ago, we observed that the distance of vertex u is less than the distance of vertex v, which means back when we chose v, we made the wrong choice, which is obviously a contradiction. So if u were in the set di, then I wouldn't have chosen this vertex v. But I did choose this vertex v, which means u cannot be a member of di. Okay, therefore, it's reasonable for me to assume that the distance of vertex u did not decrease during iteration I. Okay, that's claim 1. Claim 2. After iteration I minus 1, so before iteration I, or at the beginning of iteration I, the residual capacity of the edge uv equals 0. In other words, the residual network after iteration I minus 1 did not contain edge uv. Now this appears like it's coming out of nowhere, but the justification does establish pretty well why this has to be the case. Okay, so suppose that the residual capacity were greater than 0. What that would mean is that there is an edge in the residual network from u to v at the beginning of iteration I. Okay, but if that's the case, then we can actually say some things about the distance from S to v. The distance from S to v, so at the end of iteration I minus 1, the distance from S to v is going to be less than or equal to the distance from S to u plus 1. Because if there is an edge from u to v, then the distance from S to v cannot be any greater than this distance. It might be smaller, so there could be a shorter path from S to v for all I know. But we know that there's certainly that the shortest path from S to v can be no longer than this. That's this part of the inequality. Okay. Claim 1 told me that the distance from S to u did not change, which means that d of su plus 1 has not changed between iteration I minus 1 and iteration I. Additionally, from the way that we defined u, we know already that at iteration I, the distance to u is just 1 less than the distance to v, which means that we have that this equals this, basically. And what that shows across all of the inequalities is that the distance from S to v is less than or equal to, at iteration I minus 1, the distance from S to v is less than or equal to the distance at iteration I. And that's a contradiction, because my original assumption was that the distance went down, and this is showing me that the distance didn't go down. Okay, so claim 2 therefore must hold, because my original assumption was that the distance went down. And if there was an edge from u to v at the end of iteration I minus 1, the distance didn't go down. Okay, so what we've established is that the residual capacity from u to v is 0 at the end of iteration I minus 1, which of course implies that there is no edge between u and v in the residual network at the end of that iteration. Now, I defined that vertex u, way at the beginning, I defined that during iteration I, vertex u was the second to last vertex along a path in GFI, or sorry, not during iteration I, at the end of iteration I. Let's scroll back to remind ourselves what definition I'm talking about here. Okay, so here, in the residual network at the end of iteration I, I defined vertex u to be the vertex before vertex v along some path. I think it's reasonable to conclude, therefore, that the edge uv must be a real edge in the residual network at that point. So the edge uv is not in the residual network at the end of iteration I minus 1, but it is in the residual network at the end of iteration I. Okay, so we know that the edge uv is in the residual network at the end of iteration I, which in turn, of course, implies that there is some residual capacity along that edge. So basically what I've shown is that there was no residual capacity from u to v at the end of iteration I minus 1, but there is some residual capacity at the end of iteration I, which of course means that the residual capacity of that edge increased during iteration I. The only way for the residual capacity of uv to have increased is if I pushed some flow in the opposite direction. That's the only way residual capacity can go up from nothing. So what that's telling me is that the edge VU was part of the augmenting path at iteration I. So between iteration I minus 1 and iteration I, at the end of before the end of iteration I, the augmenting path that I chose during iteration I contained VU. So it looked like this. So if I look at the augmenting path I chose at iteration I, so we'll call that path A, and of course that's an ST path, a path from S to T, that must have passed through vertex V before it passed through vertex U, because as I mentioned a minute ago, the only way that the residual capacity UV could have increased is if I pushed some flow backwards from V to U. Now, since the augmenting path that I selected was selected with BFS, I know that the path is a shortest path from S all the way to T. Because it's an augmenting path, it's an ST path. It's the shortest ST path because I used BFS. By the subpath lemma, the part of that path from S to V must be a shortest SV path, and the part of that path from S to U through V must be a shortest SU path. And that gives us some extra information. What that tells us is, if I look at the state of the flow before I found that augmenting path, and remember that the augmenting path I found at iteration I was an augmenting path in, as it says here, in the residual network G of Fi minus 1. I'm using the flow as of the result of iteration I minus 1 to find my augmenting path that I will augment to produce the residual network GFI. Are you having fun with all this notation yet? Okay, so therefore it must be the case that the distance from S to V at the end of iteration I minus 1 is equal to the distance from S to U all minus 1, because the distance from S to V would be the length of a shortest path from S to V, and the distance from S to U would be the length of a shortest path from S to U, which, because of the edge VU appears in the augmenting path, must be 1 greater than the length of the shortest path from S to V. Okay, so I now have 3 pieces of information. I know that the distance from S to V at the end of iteration I minus 1, so during iteration I, must be equal to the distance from S to U all minus 1. Claim 1 allows us to, so recall that claim 1 tells us that the distance from S to U didn't change between iteration I and iteration I minus 1. So across those 2 iterations, the distance from S to U did not decrease. Sorry, it could have changed, but it had to have gone up, not down. And finally, from the way that I defined U to begin with, so way back on slide 91 or something, or here it is, slide 91, I have this. I have that the distance in iteration I from S to U is equal to the distance from S to V all minus 1. So I'm going to put all 3 of those pieces together. And I get this. Combining these points, I get first from slide 99, from this point here, that's my first piece, I've got that. Claim 1, I can use that to bridge this gap here. So reading from left to right, the distance at iteration I minus 1 from S to V is equal to the distance at iteration I minus 1 from S to U, all minus 1. That was from slide 99, the previous slide. Claim 1 tells me that this number and this number are both equal, which means that this thing here, or sorry, I keep saying it the wrong way. This number and this number, the thing on the left is less than or equal to the thing on the right. That's just a statement of claim 1. I can use that to sub in. I can say that the distance at iteration I minus 1 from S to U, all minus 1, is less than or equal to the distance at iteration I from S to U, all minus 1. And then slide 91, which talks about the distance from S to U and S to V at iteration I gives me this. And notice that what that's telling me here is that the distance from S to V at iteration I minus 1 is less than or equal to the distance from S to V at iteration I. That's a contradiction, because I said earlier that the distance at iteration I minus 1 was greater. I said that the distance decreased, and we know now that that is false. I want to go back to slide 91 and just quickly check something. Yeah, I think there's a little bit of a typo here. So fortunately for me, the proof is still valid. I don't know if we need this -1 here. I think the -1 might have been a typo. But don't worry, if I delete the -1, everything is still good, because what we're still showing is that the distance from S to V at iteration I minus 1 is less than or equal to the distance at iteration I. And that still contradicts this thing here. So we're still showing that we have a contradiction. Okay, so that means no such V can exist. we suppose that there were a vertex whose distance decreased at iteration I, and then we showed that no matter how we parse it, that results in a contradiction, which means the set of vertices whose distance decreases must be empty at every iteration. In other words, lemma A, which is the statement that the distance of a vertex never decreases, must be true at every iteration, and that proves lemma A. Okay, I think that was the hardest part, and that was a bit rough, especially with that little bit of a typo at the end. So this is actually a proof of what we called fact 1 earlier. This doesn't directly give us what we're looking for, but it does make the next part of our proof a great deal easier. So for the next part of our proof, what I want to talk about is edges that become fully saturated or depleted during particular augmentations. So I'm going to define a bit more terminology for that purpose. So let's suppose I'm using a particular augmenting path P. I'm going to define an edge along that path as critical if the residual capacity of the edge equals the capacity of the path. Because it was a long time since I drew this example out, I'm going to draw it again. So suppose I have some augmenting path P, which of course is a path from S to T. And suppose that I know that the capacity of this path, I'll draw it down here, suppose I know that the capacity of this path is 7 or something. Now suppose I find an edge along the path whose residual capacity is equal to 7. We're going to call this thing here a critical edge. So one way an edge can be critical is if its capacity in this direction, so pushing flow in the right direction along the edge, is equal to the capacity of the path. And this is the end, of course, when we're done the augmentation, this edge will be fully saturated. It will have 0 residual capacity. However, it's also worth noticing that because of the way that we define augmenting paths, this could also happen. I could have something like 7 out of 10 being pushed in the opposite direction. So the residual capacity in this direction here, from U to V, is still equal to 7. When I'm done the augmentation, this will have been zeroed out. I will have pushed all 7 units backwards into V. And so again, this edge is now fully depleted, and it's also a critical edge. So a critical edge is any edge whose residual capacity equals the capacity of the augmenting path in which it appears. After the augmentation, that residual capacity will be 0. Okay, so the edge will have been fully saturated or fully depleted by the augmentation. Okay, so lemma B, which is what we used to call fact 3, we're formalizing fact 3 here. Lemma B says, suppose that an edge UV is critical at some iteration I, and then later it becomes critical again at some other iteration j, and j is greater than I, that's why I said later. So iteration j is happening after iteration I. Then the distance from S to the endpoint U at iteration j, the future iteration, is at least the distance at iteration I plus 2. In other words, vertex U is now 2 further away from the source vertex than it was the last time that the edge became critical, or more. So it's at least 2 vertices further away from the source vertex. So a way of parsing this, if we go back to our fact 3, is that the distance from S to U must increase by at least 2 before the next time that the edge UV can become critical. Okay, so the proof begins with a sort of weird notational quirk that I'll explain in a minute. So suppose that an edge UV becomes critical more than once. Suppose that UV is critical at iteration I, and then let iteration j, which is a number greater than I, be the first time after iteration I that this edge appears, this edge UV or VU appears on an augmenting path. Now, that's a strange way of phrasing it because remember that in the lemma it said, suppose it's critical at I and then critical at j. But for some reason here, I'm only saying that it's critical at I and iteration j is just where it appears on an augmenting path. That is deliberate, even though it's weird. So basically, it's because it's easier to write the proof just thinking about when the next time the edge appears on a path is. I don't know whether it's going to be critical. So we know that there are plenty of times where an edge appears on an augmenting path and isn't critical. Whether that's going to happen here or not actually turns out to be irrelevant. Maybe it does always hold that the next time the edge appears on a path, it's going to be critical. I actually don't care though. I'm just saying iteration j is the first iteration after iteration I that this edge appears on an augmenting path. Now, the reason why this doesn't contradict the theorem is that if the edge is ever critical again, the earliest possible time that could happen is iteration j. It could happen much later in iteration j, but it certainly can't happen earlier, because obviously, if the edge is critical again, it has to appear on the augmenting path. So that happens at or after iteration j. So just be aware that I am conscious that my definition of iteration j here is a little bit different than in the lemma, but it doesn't change anything. I'm actually proving a little bit more general of a property than what the lemma says. Okay, so since uv is critical at iteration I, it obviously has to appear on the augmenting path for that iteration. What this is telling us, of course, is that the edge uv appears in the residual network after iteration I minus 1. So this is selected as part of the augmenting path during iteration I, which means the edge has to be in the residual network at the beginning of iteration I or the end of iteration I minus 1. Now, you just noticed me talking about iteration I and iteration I minus 1. Because of the way we chose to number the steps, because fi is the flow after iteration I, most of the discussion we're going to have about I and j in this proof is actually about f of I minus 1 or f of j minus 1. I know that that's not helping anything. That's making things even more confusing. I considered whether I wanted to change the way I numbered the steps to make this part of the proof easier, but I decided that that was not going to make things easier. If I change my definitions halfway through a long proof, it doesn't help anything. So we're going to live with this I minus 1, j minus 1 thing. So the augmenting path I choose at iteration I is based on the state of the flow at the end of iteration I minus 1. So we don't know whether uv is critical at iteration I because it's either being fully saturated or depleted, because the definition of critical we use is based on residual capacity. And we know the residual capacity of this edge could be non-zero because there is actual capacity in the forward direction, or because there is flow being pushed in the opposite backwards direction. We actually don't care. All I care about is, because this edge is critical, it has some residual capacity now. At iteration I, so it's greater than 0. However, after iteration I, if I look at the flow I get at the end of iteration I, the residual capacity will be 0. Because the edge is critical, there will be no residual capacity left after the augmentation at step I. Now, since BFS was used to find the augmenting path that I chose at iteration I, we know that that augmenting path is a shortest path from S to T. And therefore, by the subpath lemma, here it is again, by the subpath lemma, the part of that augmenting path from S to U and the part of that augmenting path from S to V are shortest SU and SV paths, respectively. So that is, if I look at my big augmenting path, the portion of it from S to V is a shortest S, or S to U is a shortest SU path, and the portion from S to V is a shortest SV path. And so therefore I know that in the middle of iteration I, or at the end of iteration I minus 1, the distance from S to V in the residual network is equal to the distance from S to U, all plus 1. Okay, so we're going to need that in a minute. Now, since uv was a critical edge at iteration I, then it's reasonable that after the end of iteration I, there is no edge from u to v in the residual network, because all of the capacity has been used up and the residual capacity is now 0. So there is no edge from u to v in GFI, which is the result of the augmentation at step I. And moreover, the edge uv isn't going to appear on an augmenting path again until this edge starts existing again, obviously. Which means the only way this edge is going to come back into existence is if some capacity from u to v gets freed up. And like we saw a minute ago with the proof of lemma A, the only time that's going to happen is when flow gets pushed from v back to u. I've got to do something to free up some capacity, and the only way to do that is to push some flow backwards into u. And of course that could happen at some point, but the key thing is there will not be an edge uv in my residual network again until I do that. Okay, so iteration j is the next iteration where either of uv or vu appear on an augmenting path. And this is why I chose iteration j not to be the next time the edge is critical, just to be the next time the edge shows up at all on an augmenting path. There is no way that either uv or vu shows up on an augmenting path between iteration I and iteration j, because of how I defined j. So iteration j is the next iteration after I where either direction of the edge appears on an augmenting path. And we know, because of what I said a minute ago, that as of iteration j, there will not be an edge from u to v, because until I push flow backwards, there is not going to be an edge from u to v in the residual network. And therefore, that means at iteration j, flow must be pushed from v to u. So iteration j is an iteration where these two vertices appear along an augmenting path. We now know that v must come first. We go to v, and then from v we go to u, pushing flow from v to u. Okay, so by the same logic as earlier, the augmenting path I chose at iteration j is a shortest path from s to t. Okay, so what that means is that at iteration j, or during iteration j, so at the end of iteration j minus 1, the distance from s to u is going to be the distance from s to v, all plus 1. Okay, and then from lemma A, we know that the distance of every vertex in the graph only increases or stays the same as iterations go on. So since j is a later iteration than iteration I, we know that the distance from s to v at iteration j is going to be greater than or equal to the distance from s to v at iteration I. Okay, so we're now going to combine together the various pieces we've come up with over the past few slides. I'll skim back over them. We have this piece here from slide 107, we have this piece here from slide 110, and then we have lemma A, so fact 1. If I combine all of those things together, we'll just read this from left to right, and I've indicated if you don't believe me, here are the slides to go check to verify these conditions. We have that the distance at iteration j from s to u is equal to the distance at iteration j from s to v, all plus 1. And we know by lemma A that the distance from s to v at iteration j is going to be greater than or equal to the distance from s to v at iteration I. Okay, so that means that this number is greater than or equal to this number. The inequality we saw on slide 107 tells us that the distance from s to v at iteration I, so at the end of iteration I minus 1, is equal to the distance from s to u at that point, all plus 1. So we can sub in this expression for this expression. And then if we just expand everything out and collect terms, we get this. So what I have shown is that the distance from s to u at iteration j is at least equal to the distance from s to u at iteration I, all plus 2. And that's actually what we were trying to prove. That's the proof of lemma B. So we've shown that the distance at iteration j from s to u is greater than or equal to the distance at iteration I from s to u, all plus 2, which is sufficient to show what we needed to show. So because iteration j is the earliest iteration where uv could become critical again, I mean, it could take a lot longer than that. It could be iteration j plus 100 where uv becomes critical again. But it's definitely not becoming critical again before iteration j. And we know that at iteration j, the distance from s to u is at least 2 greater than it was at iteration I. We also know that the distance will never go down. So that means even if the edge does not become critical again until iteration j plus 100, as of iteration j plus 100, the distance from s to u will still be at least this number. And therefore, what we know is that the next time an edge becomes critical, it will be at least 2 steps further away from the source vertex as it was the last time it became critical. All right, there's lemma B. We're ready to do it. We're ready to bring this home. So the total number of augmentations needed during the execution of the Edmonds-Karp algorithm is big O of v times z. It is a polynomial in the size of the graph. And all we have to do to complete this is to put together lemma A and lemma B with that fact 2 from earlier, the fact that every single time I have an augmenting path, at least one edge becomes critical. Okay, so by lemma B, every time a particular edge becomes critical, the distance of u, so one of the endpoints of the edge, from the source vertex S must increase by at least 2. Now, a bit of, a bureaucratic note here. Observe that on an augmenting path, we're never going to see t in the middle. So if I have S, and I've got some other vertices, I would never see the vertex. So we know that the vertex t is the end point of an augmenting path. We're never going to see vertex t in the middle. That's never going to happen. There are 2 reasons for that. So one of them is it's a path. In a path, you're not allowed to see the same vertex twice. That's not allowed. I talked about last time the fact that for all we know, there could be some algorithm out there that performs augmentations along things that aren't really paths. And so I suppose in that context, maybe we could see some algorithm out there that does an augmentation along something, a walk that involves vertex t twice. But certainly that's never going to happen during the Edmonds-Karp algorithm. Never, because we use BFS, and BFS finds actual paths that have no repeating vertices. So therefore, because vertex t never appears in the middle of an augmenting path, edges that leave vertex t will never be on an augmenting path. So t is the destination of the path. It isn't some intermediate vertex. What that means is that the vertex u, which is the starting point of the edge I'm talking about, the vertex u is never going to be equal to t. Okay, so that seems like a minor point, but we might as well fold that into our proof. So the maximum length of an augmenting path is this. We know that in a graph with n vertices, that is the maximum length you can have for any path before you have to start repeating vertices, basically by the pigeonhole principle. But since the vertex u is not equal to the vertex t, so in other words, basically what I'm saying is the vertex u cannot be the last vertex along the path, the maximum distance of u from S has to be at most this number. Because for it to be this number, that would imply that u is equal to t, which we know is not the case. Okay, so the maximum distance of a vertex u from S that it can ever be is going to be number of vertices minus 2. So therefore, after the first time that a particular edge uv becomes critical, it can become critical again at most this number of times. So here's the maximum distance I can ever reach from the source vertex, and here is the increment to the distance at each step. So every time it becomes critical, it has to become 2 vertices further away from S. Okay, so after it's been critical once, the maximum number of times it can become critical again is this number. Now, it's a strange way I phrased that. So it was critical once plus this number of additional times. So if I add the plus 1 back into that, the total number of times that a particular edge uv can be critical is this number. Number of vertices all over 2. Okay, so then we bring back fact 2. Fact 2 said that at least one edge must be critical on every augmenting path. So we know that because of the way we define the capacity of the path, the total number of units of flow that we push along the path at each step, because the value of CF of P is defined to be the minimum value of residual capacity among the edges of P, that means that at least one edge is going to be fully saturated or depleted after every augmentation. In other words, at least one edge must be critical on every augmenting path. So in the worst case, we know now that for every edge, there is a maximum number of times it can become critical. It is this number here. We also know that every augmenting path must have at least one critical edge. So if, in the worst case, if every single edge appears on the maximum possible number of augmenting paths, then the total number of augmenting paths can be at most this. So for every single edge, that edge appears on this number of augmenting paths. Well, I can never choose any more than this number of augmenting paths without having an edge appear too many times. So the total number of augmenting paths is v times e all over 2. And therefore, if we ignore that over 2, the total number of augmentations is big O of v times e. Now, I'm using a big O here because I haven't proven that this is actually always required. I've only proven that certainly there's no way any edge can appear on more than a certain number of augmenting paths. I haven't shown that there's a graph where every single edge always appears on the maximum number, which is why I'm using a big O instead of a big theta. However, a big O is good enough for getting an upper bound. All right, are we ready? This is it. We're about to conclude the most complicated proof of the course. So, the theorem is that the running time of the Edmonds-Karp algorithm is v times e squared. So we've already established in the previous lecture that performing a single augmentation, so that involves finding the augmenting path and actually walking along the path and doing the modification to the flow, a single augmentation requires big theta of e time. And since this is the number of augmentations needed in the worst case, the total running time of the algorithm is big O of v times e squared. So the Edmonds-Karp algorithm is able to find a maximum flow of a flow network in polynomial time in the size of the network. There it is. Okay, it's all downhill from here. So we just spent all of this time talking about and stumbling over the proof that the Edmonds-Karp algorithm is polynomial. I suppose we owe it to ourselves to take a victory lap and run the Edmonds-Karp algorithm. So compute a maximum flow for this flow network that we've used as an example a few other times during this lecture using the Edmonds-Karp algorithm. Let's just watch this go. Okay, our first augmenting path has length 4, and it increases the flow value by 2. Our second augmenting path has length 4 as well and increases the value by 1. Our third augmenting path, we can see 1, 2, 3, 4, 5. It has length 5. It increases the value by 3. Our fourth augmenting path increases the value by 4. And we're done. We already know that the maximum value of this flow is 10. And we also know that we have a cut here with total capacity 10. And so by the max flow min cut theorem, we know that we have a maximum flow and a minimum cut. Maybe that was too easy, though, because we already knew the answer for that graph. Here's a really messy-looking jumbled graph. Let's use the Edmonds-Karp algorithm to compute a maximum flow for this. And I encourage you to pause the video and try it out, because once you see the right answer, maybe it's not so authentic to compute it yourself. Okay, so our first augmenting path here has length 4. There's our second augmenting path, also length 4. Another one with length 4, another one with length 4, another one with length 4. Then we get into the 5s. Here's our first augmenting path of length 5. There's another augmenting path of length 5, a third augmenting path of length 5. Now we begin getting into some weird cases. So here is an augmenting path of length 1, 2, 3, 4, 5, 6, 7. Okay, notice that this augmenting path does have to push some flow backwards along one of our edges. Okay, and then one more. Here's an augmenting path, another one of length, so 1, 2, 3, 4, 5, 6, 7, 8. Here we have an augmenting path of length 8. And notice how this fully depletes this backwards edge. So I can't push any more flow backwards along this edge. And it turns out that we've now reached a maximum flow. How do we know? So it has value 14. How do we know that it's maximum? Well, we just try running one more step of the algorithm. We take a look what vertices I can reach by edges that are not saturated. So I can get to S, V2, V5, and V3. And that provides us a cut. If I look at the capacity of that cut, it's 3 plus 4 is 7, plus 3 is 10, plus 1 is 11, plus 1 is 12, plus 2 is 14. So I found a cut with capacity 14. That is the same as the value of my flow. So I have a maximum flow and a minimum cut. There it is. And we found a way of solving the maximum flow problem in polynomial time. And oh, yeah, that's right. And we still have that fire to put out. But you know what? I think, that's a great way of just wrapping this whole thing up. So we at the beginning, I said we can't put that fire out until we know what we're doing. But we know what we're doing now. We know what a maximum flow is. We have a source vertex, a sink vertex. We run the Edmonds-Karp algorithm to find a flow in polynomial time. We know that we can find a minimum cut that matches the value of our maximum flow, which proves that the flow is maximum. And so now we can charge in like the heroes we are and finally start putting